we do this, we had f of x equals negative 2 x minus 2 plus 4. So we're asked to graph this function. So obviously the base is 2 to the x. The first transformation is 2 to x minus 2, which is right 2. Number 2, Emmy, any questions? Okay, so then we have a reflection, reflect with respect to the x-axis. And number 3, up 4. So negative 2 x minus 2 plus 4, up 4. So when you graph it, 2 to the x, because the base is greater than 1, is a function increasing on all its domain and definitely crossing at 1. So this is 0, 1. So this is 2 to the x. Then we shift it 2 units to the right. So that reference point is all I need. So this will be 2 to x minus 2. Then we reflect this, and this point moves to negative 1. So this is the negative 2 to x minus 2. And now when I move up, if I don't move the horizontal asymptote, I can't get full credit. I have to move the horizontal asymptote first, up 4. So 1, 2, 3. I have to draw the horizontal asymptote at 4. And then I move this point here. And that's done. So this is the final graph of negative 2x to 2 to x minus 2 and plus 4. And now I identify that the range is negative infinity to 4. And of course, the domain is all real numbers. So that's one. Now, in order to find the x and y intercepts for this, I determine f of 0, which will be negative 2 raised to negative 2 plus 4, which is negative 1 over 4 plus 4, which is 16 minus 1, which is 15 over 4. So 0, 15 fourth will be the y-intercept. Now, the x-intercept is when y is 0. So negative 2 x minus 2 plus 4 equals 0. I move 4. Multiply by negative 1. 2 to x minus 2 equals 2 squared. So x minus 2 has to equal 2, or x equals 4. So 4, 0 is the x-intercept. So this is 4, 0, and this is 0, 15 over 4. So that was the graph. Then the equation, natural log of 2x minus 1 minus natural log of x plus 3 equals natural log 4. That one requires, if you check, you don't have to state domain. But I prefer for this one to state a domain. And x plus 3 greater than 0. So from here, x is greater than 1/2, and from here, x is greater than negative 3. So of course, domain is 1/2 to infinity. Then I condense the left-hand side, which is natural log of 2x minus 1 over x plus 3 equals natural log 4. And this is exactly what Sarmat asked an hour ago, half an hour ago. So 2x minus 1 over x plus 3 equals 4. And we cross multiply. 2x minus 1 equals 4x plus 12. Negative 2x equals 13. X equals negative 13/2. That was one. Now the other form, we were given the model, of course, 1 plus r over n raised to nt. And we were given two conditions. So this was 6,000. T was 5 years. And the interest rate was once 0.0825 compounded quarterly, which means n is 4. And the other one was 0.083 compounded semi-annually, which n is 2. I have no idea what this gives, so I have to use the calculator. So I have 6,000 in parentheses 1 plus 0.0825, and this one is divided by 4. And the power is 4 times 5, which is 20. So this is 9,025 for the first one. 9025.58. Any questions? Yes? Any questions? Yes, please.
Why is it divided by 4 again?
It says compounded quarterly. And the second one, it was compounded semi-annually. and it was 8.3. So this is 3. Let's see if it works. Okay, and the power now is 2 times 5, which is 10. So the second one is 9. So A2 is 9010.40. So therefore, based on this, any questions, Bailey, please?
No.
From this, the first one is more advantageous for us because we get a little bit more. So when the interest, even if the interest is a little bit lower, but compounded 4 times a year, it comes out to be a better deal for us. And the last problem, so this is 6. Okay, last problem was 1/27 to power 2x minus 1 equals 81 to power 1 minus 3x. And this is 3 to negative 3, 2x minus 1, and this is 3 to the 4th to 1 minus 3x. So 3 to negative 6x plus 3 equals 3 to 4 minus 12x. Obviously, the powers have to be the same. So this is 6x, and this is 1, so x equals 1/6. Okay, so moving on. Any questions? Any questions? Okay, so let's move on. We are starting trig today. So let's talk about angles. So chapter 7. So 7.1, we're talking about angles. There are several types of angles that we need to review or look at. So first of all, positive and negative angles. That's one category. Positive, negative angles. That's our first step. Okay. This angle, let's call it alpha. We're going to use a lot of Greek letters here. So this is in geometry and trig. Alpha is a positive angle. This is its initial side. This is called terminal side. Counterclockwise angles are considered positive. Here's a negative angle. This is its initial side. Let's say this is its terminal side.
That's supposed to be a little fish side. 7. That's alpha.
Yes. So, yes, this is alpha. This is beta. Alpha, beta, and we'll have more. So the second angle has the initial side on the x-axis, the terminal side somewhere in the third quadrant, and this is a negative angle. I hope this is not news, but let me also make sure that it's clear. This is the first quadrant, this is the second quadrant, this is the third quadrant, and this is the fourth quadrant. Counterclockwise, 1, 2, 3, 4. So we say, for example, angle beta starts on the x-axis and has its terminal side in the third quadrant. Angle alpha has its initial side on the x-axis and a terminal side in the first quadrant. So this is one thing. Positive and negative angles. Angles in standard position or form. Both angles that I just shown here in the first two examples are both in standard position, meaning the initial side is on the x-axis and the terminal side anywhere in the first, second, third, or fourth quadrants. All these both are in standard position. So one more time, an angle in standard position, this is to give you another example, is this. Its initial side on the x-axis and the terminal side anywhere. And this is gamma. The measure of this angle, or angle gamma. Okay. Now, one of the the most important concepts here is the reference angle. Everything depends on the reference angle. Okay, so reference angle. I'm going to select an angle in standard position with the terminal side in the first quadrant. And I'm going to show other positions with the other angles in standard position with terminal side in the other quadrants in a minute. So this is angle alpha, let's say. The reference angle, let me explain what the reference angle is and we can write it down. The shortest angle, the smallest angle between the terminal side and the x-axis. Is it this or is it this? It's a silly question, I know. So it happens that this angle, because it's in standard position and has the terminal side in the first quadrant, it's its own reference angle. The smallest angle between the terminal side and the x-axis. The acute angle, to be exact.
That's what a reference angle is?
Yes. So the reference angle, I need an L here. The reference angle is the acute, which means less than 90 degrees. The acute angle formed between the terminal side of the angle and the x-axis. In this case, this is also a reference angle, RA. Here's another example when the angle has a terminal side in the second quadrant. Standard position. This is, let's say, angle theta. Angle theta. It has its terminal side in the second quadrant. And the acute angle formed between the terminal side and the x-axis is this piece. This is the reference angle for angle theta. Let's look at the other two possibilities. When the reference angle has a terminal side in the third or the fourth. So let's say this is angle beta, and the reference angle is this. The acute angle formed between the terminal side and the x-axis. Any questions so far?
Yeah, how do you pick the gamma sign?
The gamma?
Yeah.
Very good. Yes. Yes.
So why wouldn't the reference angle be the other way?
This one?
Yeah. No, why wouldn't it be like that piece of the side quadrant?
You mean this one?
Yes. Oh, okay.
Clear?
Yeah.
Perfect. So now let's look at the last possibility. Let's say angle theta. The reference angle is this. How do we measure angles? We measure angles in radians or degrees. Okay, let's start with degrees. Complete circle has how many degrees? Very good, 360 degrees. Now, let's assume that this is a circle with a radius 1. Has a special name, of course. It's called the unit circle. Let's say the radius is 1. Here's a question for you. What is the circumference of this circle? What is the formula for the circumference? Let me give it to you. It's 2 pi r. But if the radius is 1, this specific circle with the radius 1 has the circumference 2 pi. Okay? But this is the same thing with 360 degrees. Would you agree? Okay, if 2 pi equals 360 degrees, then pi is definitely 180 degrees. This is a relationship between radians and degrees. Relationship between radians and degrees. But now what if I want to determine 1 radian? Not pi radians, but I want to determine 1 radian. What should I do to both sides to get 1 radian? Not 3.14 radians. I want just 1. What should I do to both sides of the equation to get just divide by pi? Very good. Thank you very much. So 1 radian is the same with 180 over pi. What if I want this side? What if I want 1 degree? What will 1 degree, not 180 degrees, look like or equal to? What should I do to both sides to get 1 on this side? Not 180. I just want 1. What should I do? Here I had pi radians. In order to determine 1, I divided both sides by pi. Now I have 180 degrees, but I want just 1 degree. What should I do to both sides to get 1 degree? Right, exactly. Exactly. So this is the relationship whenever you need to change 1 radian into degrees and when you want to change 1 degree into radians. All you have to remember, you don't have to remember this, ever. All you have to remember is this. And I'll help you remember that in a minute. So let's go back to what we call the unit circle. Do I go back? Do I need to go back? Do I need to go back here? No? Okay. So let's go back to the unit circle. So these are only the preliminaries, right? We need all this information to continue. Okay, so we already know now that this is 0 degrees or 0 radians. If nothing follows, it means 0. If it's 0, it means radians. Otherwise, you would have the little circle for representing degrees. Also, 360 degrees, this point right here, and also 2 pi. That little point represents 0 degrees, 360 degrees, 0 radians, or 2 pi radians. The one exactly opposite of it, what does that represent? Yes, this represents pi radians, at the same time 180 degrees. What does this point here represent? You know what I mean by that, I mean this angle, right? And what I mean by this, I mean this angle, of course. So this one is in radians, very good, pi over 2, and in degrees, of course, 90 degrees. Last one here. Very good. So this is indeed 3 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, right? Or 270 degrees. Very good. Perfect. The most important angles that we're going to look at, in addition to these, they're called kind of corner angles. Of course, there is no corner there, but you know what I mean. So on the unit circle, or any circle actually, are in both degrees and radians. 30 degrees, 45 degrees, and 60 degrees. So these are in degrees. How do I get them in radians? Very easy. So the 30, it's basically a third of the first quadrant or any quadrant. 30, 30, 30. So it's basically pi over 2 divided by 3, right? Which is pi over 6. 45 is exactly in the middle, so it must be this divided by 2. Indeed. And 60 degrees, well, we have 3 60 degrees in here, so it must be pi over 3. 360 degrees, so it's pi over 3. Sometimes when we are asked, for example, find the trig functions for 5 pi over 6. Well, it may be difficult to think in radian terms. That's okay, but 5 pi over 6 will be 5 of 30 degrees. So we're going to come back and fill this in, hopefully today, with sine and cosine. Not now, we don't have the information just yet. We are still in the preliminary stages. Okay, so I recommend, for example, if we're asked to look at 5 pi over 6, just imagine that this is 5 multiplied by 30 degrees, which is 150 degrees. Where will this land? Where will it have its terminal side? Well, obviously, 30 degrees short of 180. Right here. 30 degrees short of 180. So this will be 5 pi over 6. Can anyone give us the reference angle? Yes. Or pi over 6. Very good. Excellent. Okay, let's try another. Let's say 4 pi over 3. What does that mean? Well, it means 4 multiplied by 60, which is 240. Where does this land? Well, 60 degrees beyond 180, correct? So this is 180. Here is 60 degrees right here. This will be 4 pi over 3. Can anyone give us the reference angle? Yes. Pi over 3 is the reference angle. Do we understand how this works? Yes. So 4 pi over 3 is 240 degrees. So this is 180, and this is 240. The difference must be 60.
Yeah, so, and 60 is pi over 3.
Pi over 3. 60 is pi over 3. How do you know? 180 over 3. 60 degrees. Very good. Okay, so let's look now at the area of a sector, and basically the first is the arc length. So let's say we have a center angle. What does a center angle mean? It can be this angle. It doesn't have to be in the standard form. This is angle alpha. It doesn't have to be in the standard form. It's a center angle. Its vertex is in the center of the circle. And let's suppose we're asked to determine this length, the arc length, denoted by S. The radius is denoted by R. The formula for the arc length is R times theta, or alpha. Alpha times R. In your book, I think it's S. Theta times R is the same thing. If you want to change alpha into theta, it's the same thing. Any notation. So the length of the arc is theta times r. However, there is a catch here.
What is that? Is that supposed to be an S?
This is, yes, the length, the arc length, uppercase S. The angle must be in radians. The formula does not work if the angle is not in radians. Okay, let's look at a couple of problems now. Okay. Problem 40, for example. Let's read it together. Find the length of the arc of a circle of radius 12 inches, subtended. Subtended is right here. It's the opening of the circle subtends the arc. Okay, subtended by a central angle of pi over 4 radians. So let's copy the information down. So this is problem 40, page 591. And we have the radius equals 12 inches. And we have the angle, let's say theta or alpha, whatever, it doesn't matter, pi over 4. It is in radians? Yes. Arthur, you have a question? Okay. Theta times r, so this is 12 times pi over 4 or 3 pi after you simplify. Yes, we can plug it in and just, oops, sorry. We can plug it in and approximate it if that's what you want. Let's take a look at the area of the sector now. A circular sector. Circular sector. For example, this is a circular sector. And if we want to determine the area, this is 1/2 r squared times theta. Theta being the angle that subtends the arc of the circle, the central angle. So let's find for the following exercises, use the given information to find the area of the sector. 46. A sector of a circle has a central angle of 45 degrees and a radius of 6. So 46, page 592. So we are told that the angle, alpha, theta, it doesn't matter, 45 degrees, and a radius of 6 centimeters. We're asked to find the area of that circular sector. How do we write this? 1/2 times the radius squared, which is 36, times 45 times 1 degree in radians. 180 over, so remember 1 degree. 1 degree is pi over 180. 1 radian is 180 over pi. So we want to change 1 degree into pi over 180. So times pi over 180. So we can simplify and then multiply and get a number here, or simplify first. Any questions? So that's 4.
The area in degrees, is that why you add that? No, in radians.
Yes. The formula doesn't work. None of these formulas, I didn't mention it here, but theta must be in radians. The same thing here. Theta must be in radians for the center, for the arc length. Theta must be in radians for the area. Theta must be in radians. Formulas don't work with degrees. So we changed 45 degrees into 45 times 1 degree, and 1 degree is pi over 80. Is that clear? Is that clear? Yes, Bailey?
12 equals 6.
the radius has to be squared,
Oh, that's hard. You're right.
36.
No,
And then theta, which is 45.
Wait, that's a R.
Yeah.
Oh, R equals 6.
Yes, the radius equals 6. Okay, so 180 divided by 45 is 4. And this is 9. So I see 9 pi over 2, whatever units squared. That's the area. Any questions? Any questions? Yes, David, go ahead. Is this clear? Yes?
Wait, so you did 45 times pi over 8.8, right?
So I have the 1/2. I have the radius squared, which is 36. I have the angle, which is given to us as 45 degrees.
And you have to turn that into radians, which you said.
Yes. 1 degree is pi over 1/8.
518, and so you did 45 times.
Everything's multiplied. 1/2 times r squared times theta.
But where did you get 45 degrees into
Radians.
radians? You did 45 times pi over 8.
Right.
Because that cancels out your degrees and gives you only radians.
And then you got pi over 4.
Because she was
I
just.
simplify by 45. 45 divided by 45 is 1. 180 divided by 45 is 4.
And then she did it again.
Yes.
And 4 divided by 4 is 1. 36 divided by 4 is 9.
Just look here all together.
Okay, well, simplify it in your own order. You don't have to use mine. But is it better? Is it clear now? Any questions? Okay. Did I answer your question?
Is that unit squared or is that centimeters?
Yeah, whatever it is. We were given centimeters, yes? Centimeters then. Centimeters squared. And in that case, let me go back because I'm very keen on measurement units. So let me be clear and accurate and put them everywhere they should be. Okay. 7.2. At the right triangle trig. The right triangle. Okay, so let's take a look at a right triangle. Yes, any questions in the back? Amy, go ahead.
No.
Okay, Lauren, anything? Okay, so here's a right triangle. We're going to denote the sides by A, B, and C. And we're going to talk about this angle. Which letter you would like to use, it doesn't matter. Which one is easier to write?
Theta.
Theta. Very good. We're going to define 6 trig functions. 6 trig functions. Sine theta, cosine theta, tangent theta, cotangent theta, secant theta, and cosecant theta. Okay, by definition, sine is the opposite leg, opposite to theta, over the hypotenuse. So this is A divided by C. By definition, cosine, do you want me to write opposite over hypotenuse? Very good. Opposite over the hypotenuse. Cosine is the adjacent leg over the hypotenuse. So that will be B divided by C. Adjacent leg. Adjacent leg over the hypotenuse. Tangent will be opposite over the adjacent. Now you know what they are, A, B, and C. Cotangent is the adjacent divided by the opposite. Secant is 1 over cosine, so it will be C divided by B. And cosecant is 1 over sine, and I'm going to write the relationship in a moment, is C divided by A. Now the relationships between the trig functions. Tangent theta is 1 over cotangent theta, and also is sine theta over cosine theta. Of course, cotangent theta is 1 over tangent theta, and also cosine theta over sine theta. Secant and cosecant. 1 over cosine theta, and cosecant is 1 over sine. So if the function starts with S, in the denominator it has C. If it starts with C, in the denominator it has S. If you like to remember it like that. There are many other relationships between these three functions, but we're not ready for that yet. When we get to the next step in the unit circle, we're going to look at the other ones. Let's suppose now we have what we call a 30, 60, 90 degree right triangle. 30, 60, 90 degree right triangle, where we have A and B and C. We're trying to determine the trig functions for these important angles, and then we're going to look at an isosceles right triangle, of course, for the angle 45. There is some piece of information that we know about the 30, 60, 90 degree right triangle, specifically about the relationship between the opposite leg of the 30 degree angle and the hypotenuse. So in a 30, 60, 90 degree right triangle, there is a very specific relationship between the opposite of the leg of 30, of the angle of 30, and the hypotenuse. Anyone remembers the relationship between these two? It's okay if you don't. This piece must equal 1/2 of the hypotenuse. Only in the 30, 60, 90 degree right triangle. So this piece will equal 1/2 of C at all times.
The A equals 1/2 C.
Yes, only in the 30, 60, 90 degree right triangle. So then, if that's the case, how much is sine 30 degrees, which is the opposite over the hypotenuse? A divided by C. If A is 1/2 C, and C is in the denominator, and they cannot be 0, C cannot be 0, what is always forever sine 30 degrees? So now we can go back to our table that we started a few minutes ago, and we can fill in for 30 degrees or pi over 6, what is sine? What does sine equal to? 1/2. Any questions? Any questions? Okay. Now we want to identify cosine of 60 degrees. So you can say you haven't finished with 30 in a minute. So let's identify cosine 30 degrees, cosine 60 degrees. So then cosine 60 degrees will be the adjacent leg over the hypotenuse. But we've seen the adjacent leg over hypotenuse a minute ago. What does that equal to? A divided by C. What does that equal to? 1/2. Agreed? Same thing. So sine 30 degrees is the opposite over the hypotenuse, but so is cosine 60 degrees, the adjacent over the hypotenuse. So we go back to our table and we jump to 60 degrees, pi over 3, right here. 1/2, 1/2. Any questions? Okay, back to our triangle. If I know that this is C, and this is 1/2 C, and this is B, 30 degrees again, I'm just copying it one more time. Let's identify cosine 30 degrees. Cosine 30 degrees is B over C. Would you agree with that? Okay, what else do we know in a right triangle? Always. There is a theorem that we always apply in a right triangle. Yes, but careful. Don't say that. Say the hypotenuse squared equals the sum of the squares of the two legs. Because if you say A, B, and C, or A squared equals, you have to specify which one is the leg, or which one is the hypotenuse, and which ones are the leg, the two legs of the right triangle. Okay, so then this is C squared equals 1/4 C squared plus B squared. From here, C squared minus 1/4 will be 3/4 C squared equals B squared. I just want to find B and put it in here to identify cosine 30. So when we take the square root from both sides, B will be the square root of 3 over 2 times C. Take a moment and see if you understand all steps here. Is this clear? So from this triangle where I know that this is half of C, I have B, I have C. I wrote the Pythagorean Theorem as you told me. The hypotenuse squared equals this leg squared plus this leg squared. I squared them. I got 1/4 C squared plus B squared. From C squared, because I moved this term to the left-hand side, from 1 I subtract 1/4 to get 3/4. And I take square root from both sides. Of course, it's all over. It's not, sorry, it's all the way. So then B is the square root of 3 over 2 times C. Would you agree so far? Knowing this, I'm going to replace B. So then cosine 30 degrees is B, which is the square root of 3 over 2C divided by C. And then what happens then? So how much is cosine 30 degrees? Square root of 3 over 2. And we can go back now to our table and put that cosine 30 degrees is the square root of 3 over 2. Now, by symmetry, what do you think this will equal to? So then we know already the square root of 3 over 2. Now we have to look at these two. So let's take a look at an isosceles right triangle, meaning A, and C. 45 degrees, 45 degrees, or pi over 4. Isosceles right triangle. Isosceles right triangle has two angles that have the same measure, and two sides, the legs, have the same measure. So then, we want to determine sine 45 degrees. That will be A divided by C. From the Pythagorean theorem, we have that C squared equals A squared plus A squared. From here, I'm going to solve for A. So C squared equals 2A squared. And take the square root. I prefer to divide first. It's the same thing. So let's divide. So this is A squared equals C squared over 2. And now we take the square root. And we get A equals C over the square root of 2. We need to rationalize. So A equals C the square root of 2 over 2. That's all I needed. I need to go back. Sine 45 degrees equals C the square root of 2 over C. And we determined that the square root of 2 over 2 is sine of 45, as well as, and this is the only angle for which sine and cosine are equal. So the square root of 2 over 2, the square root of 2 over 2. Questions? But now, the most important step is, once we discovered what happens to 30 degrees, 45, and 60, now we're able to determine sine, cosine, or any trig function of any angle you can think of. So now, make up an angle, please. Or I can make one up, or I can use problems from here. Okay, so let's say theta equals 5 pi over 4. We're asked to find all trig functions. Find all trig functions of theta. Okay, so first we have to locate it. Locate the angle. Where is it? I have no idea. In a moment, we'll find out. What does 5 pi over 4 mean? I don't know, but I know that pi over 4 is 45, and there are 5 of those. 1 here, second, third, fourth, fifth. 5 of half of quadrant. So this must be it. This is it. This is the 5 pi over 4. Let's take a look at the reference angle. Can anyone give us the reference angle? Please. 45. Excellent. So this is the reference angle. Pi over 4 indeed. Here's what I'm going to do next. I'm going to create a right triangle and determine sine and cosine for pi over 4. But we know the sine and cosine for pi over 4. We know that sine pi over 4 is very good. And we know that cosine pi over 4 is. But you can say, wait a minute, and I'll say yes. The angle has the terminal side in the third quadrant. In the third quadrant. So if it were in the terminal side were in the first quadrant, obviously everything would have been positive. Both sine and cosine would have been positive, because this is the positive side of x, this is the positive side of y. But the angle has the terminal side in the third quadrant. That means that this little piece is the cosine, but it's in the negative side of the x-axis. So then this must be sine 5 pi over 4 must equal negative the square root of 2 over 2, not positive, because the terminal side of the angle is in the third quadrant. What about So this was the cosine. What about sine? Sine is this piece. It's below the x-axis. So therefore, cosine of 5 pi over 4 is also negative the square root of 2 over 2. Because the terminal side of the angle is in the third quadrant. What if the terminal, we're going to look at another example. What if the terminal side would have been here in the second quadrant? Which of these two, sine and cosine, would have been negative? Cosine would have been negative, but sine would have been positive. Excellent. So make up another angle. So now we want to determine the other ones. I do not recommend, but that's my suggestion to you. I do not recommend remembering anything more than this. There is no point. It will take you 20 seconds to determine the rest for any angle you want. So for example, we're finishing up with 45, right? With 5 pi over 4. I don't care for anything else. The table should not, you just should not sit there and memorize these numbers. Nothing else other than 1/2, the square root of 3 over 2, the square root of 3 over 2, and the square root of 2 over 2 for both. So in this case, the question is asking us to also determine the other trig functions. Fine. I know that tangent theta, 5 pi over 4 I meant, is sine over cosine. So this must be 1. What about cotangent? What about cotangent of 5 pi over 4? Yes, cotangent 5 pi over 4 must be 1. What about secant 5 pi over 4? Secant is 1 over cosine. I have to flip. Yes, it will be negative 2 over the square root of 2, but now I have to rationalize again. And these will be gone, so the answer would have been negative the square root of 2. Finally, cosecant 5 pi over 4. For this angle, it will be the same. I don't, as I said, I don't recommend, and I do this with my calculus classes as well. I refresh their memory. This is just a tiny little bit of 3 numbers that you have to remember. Do not remember anything else. It will get fuzzy at some point in time. Okay, let's make up another angle. Any angle in any quadrant that you would like to work with.